Sometime in the not too distant future, a spacecraft will leave Earth orbit and head out across the solar system. Its destination, Mars, the only planet in the solar system where we stand a chance of establishing a foothold, where we might be able to live even in an extremely dangerous environment. And for more than 100 years, we've dreamed of walking on its surface. Mars is reminiscent of deserts on Earth. It's completely dry, no water has flowed across its surface, nor formed lakes or seas for billions of years. It has huge canyons, rolling sand dunes, ancient river valleys. But while it might look familiar, Mars poses a level of danger to humans unlike anything we've ever experienced on Earth. There are many ways of dying on Mars. Future explorers will live on a knife edge where one tiny mistake can have fatal consequences, where just staying alive will be a constant struggle. So what dangers will future Mars explorers face, and why is Mars such a dangerous planet? Assuming that astronauts have survived the physical and psychological challenges of a 6-month journey to Mars, far longer than any crewed space mission beyond Earth orbit ever attempted, the most dangerous hazard they will face is radiation, charged particles from the Sun and the wider galaxy. Mars has no global magnetic field to shield astronauts from solar and galactic radiation as we have on the Earth. It's estimated that a 3-year round trip to Mars will give astronauts, if they're not adequately protected, radiation doses above the safe limit for their entire lifetime. To put it another way, each unprotected astronaut on Mars would receive the equivalent of 7 chest X-rays during one Martian day. Prolonged exposure to solar and galactic radiation can lead to nausea, sickness, and ultimately death. So spacesuits would have to be lined with materials which can block at least some of the radiation. NASA are experimenting with a material called Demron, which can do just this. It could be incorporated into both spacesuits and the structure of a Martian base, as well as garments astronauts might wear inside the base. As yet, however, there's no data as to how effective Demron is against harmful levels of radiation, but it is thought to be promising. Even so, astronauts will probably need to be outside for limited periods, as any protection in their suits will not block all the harmful radiation. Their base will need extremely high levels of protection. But is there an alternative to the domes of a future Mars base being constantly exposed to the potentially lethal charged particles raining down from the Martian sky? This is the entrance or skylight of a collapsed lava tube on Mars, as imaged by NASA's Mars Reconnaissance Orbiter, or MRO. It dates from Mars' volcanic past, billions of years ago before the core of Mars froze and all volcanic activity ceased. Radar surveys indicate these lava tubes, several dozen have so far been identified, are at least several tens of meters deep and extend underground in tubes which may be hundreds of meters wide. The skylights themselves are also several tens of meters across. These lava tubes would be an ideal place for a future Mars base, shielded from the solar and galactic radiation by tens of meters of solid rock. However, this would not be the first base on Mars, but rather a long-term solution. Before a base could be built underground, extensive surveys by ground-penetrating radar and robotic vehicles would be required before any astronauts could descend into the depths, and this could only happen after an initial base were established on the surface. A crewed mission to Mars will embark upon a journey which will last for a minimum of 2.5 years. This is not by choice, but because Earth and Mars align only every 2 years, so that the journey to the red planet can be cut down to 6 months. At this point, when the two planets are at closest approach, they are between 50 and 60 million kilometers apart. The mission profile would therefore be a 6-month journey to the red planet, then 18 months spent on the Martian surface to await the next alignment of the planets, followed by a return to Earth lasting another 6 months, a total time of 2.5 years. This is the shortest possible duration for a mission to Mars with current technology. But what effects will such a long journey, such prolonged isolation, have on the human mind? Since the beginning of manned spaceflight, scientists have studied the effects of long-duration space missions on the human mind, but these experiments only started in earnest after the construction of the International Space Station, which has become an orbiting laboratory for studying the physiological and psychological effects of prolonged space missions on the body and mind. In general, the studies have shown that astronauts can experience a range of psychological challenges during long missions. These can include feelings of isolation, disrupted sleep patterns, and sometimes even mood changes. However, the studies have also shown that with the right support systems like communication with family, structured schedules, and engaging tasks, astronauts adapt quite well. However, the longest that anybody has spent on the ISS is 371 days, a record held by astronaut Frank Rubio. This is obviously far short of the 2.5-year duration of a mission to Mars. But there has been an attempt to understand the psychological effects of longer duration space missions. It was called the Mars 500 experiment. The Mars 500 experiment, carried out between 2010 and 2011, was a ground-based simulation designed to replicate a full-length mission to Mars. It involved 6 crew members living and working in an isolated, confined environment for 520 days. The experiment used 5 interconnected modules with a total volume of about 550 cubic meters. The main habitat module itself was roughly 3.6 meters in diameter and 20 meters long, providing living quarters for the 6 crew members. The facility also included a medical area, a storage module, and even a simulated Martian surface module. The objectives were to study the psychological and physiological effects of long-duration spaceflights. The results showed that while the crew experienced some challenges like monotony and sleep disruption, overall they adapted well, providing valuable insights for future Mars missions. But as the first Mars astronauts watched the Earth slowly receding, as everything they have ever known shrinks behind them, as they begin to sense the infinite vastness of space, how will they feel knowing they will not return for years? As the gaps in the radio chatter get longer and longer until it becomes impossible to have a conversation with their loved ones, will the weight of their total isolation bear down hard on them? They will have been selected for both their physical and psychological resilience, but no human beings will ever have been more alone, so cut off from their lives on the Earth. There will be no door of a prison cell that can be thrust open to let the daylight stream in, no blindfold that can be removed to escape the darkness. When the Earth becomes just a distant blue dot among the stars, nobody really knows what that will do to the human mind. Can any amount of training truly prepare them for this? During the days and weeks following the Mars landing, the astronauts will be kept constantly occupied, requiring immense amounts of coordination and teamwork to build a habitat. They will probably push their possible feelings of isolation to the back of their minds during this intensely busy period. The astronauts will need to acclimatise to working in gravity that is only 38% of the Earth's, learning how to move around deliberately and safely. One fall on a jagged rock could be fatal if it were to rip open their spacesuit. So how far they are from the Earth, how isolated, and how they will face the long haul ahead, the 18 months before they can return home, will doubtless not be prominent in their minds. But when they are alone during those long months with time to reflect, how might feelings of loneliness and isolation prey on their minds? Only the very toughest of minds will be able to deal with these emotions. Psychological support for the astronauts, therefore, is going to be a crucial part of the mission. At the end of the day, however, we will be very much in uncharted territory. This is British astronaut Tim Peake doing an experiment on the International Space Station to see if he can make himself dizzy. The answer is, somewhat surprisingly, that he could not. When astronauts first arrive on the ISS, they often do feel dizzy and nauseous because their vestibular system, the liquid in the inner ear which, acting like a gyroscope, tells your brain which way is up and therefore allows you to balance, is contradicting what the astronaut is actually seeing. However, after a couple of days of eyes and ears contradicting each other, the brain shuts the vestibular system down and relies instead on visual cues to establish orientation. This is why Tim Peake didn't get dizzy. While the dizziness and nausea are perhaps a temporary inconvenience for astronauts, these effects of being in a microgravity environment are minor compared with more lasting and damaging physiological effects that can be suffered during a long-duration space mission. Floating in space might look fun, but it's potentially extremely harmful to humans. There are many physiological effects caused by prolonged periods in microgravity. Most severe are muscle loss and bone weakness. To combat these, astronauts on the International Space Station must perform long periods of exercise every day. When they return to Earth, they are often unable to stand, and they experience several days of readjustment to normal gravity. One way of combating the adverse physiological effects of microgravity is to rotate the spaceship or space station, as depicted here in the classic film 2001: A Space Odyssey, in order to provide artificial gravity. How much gravity could such a rotating structure generate? It depends on two factors: the rate of rotation and the diameter of the structure. As for the rotation rate, 2 rotations per minute would be a comfortable speed so as not to disorientate the crew. Such a structure attached to a spaceship bound for Mars would need to be 448 meters in diameter to provide 1 g of gravity, in other words the same gravity as on the Earth. That would be a huge construction. On the other hand, if you wanted to generate just a third of Earth's gravity, the diameter required for the rotating structure would shrink to just 75 meters. A third of Earth's gravity would greatly lessen the adverse physiological effects on the astronauts. Coincidentally, a rotating structure of around the 75-meter diameter size was portrayed in the marvelous sequel to 2001, 2010, the year we make contact. It provided artificial gravity on a Russian spaceship headed for Jupiter. Generating a third of Earth's gravity would mean that the astronauts, instead of having to exercise for 2.5 hours daily as a minimum to remain healthy, as they currently have to do on the ISS, might have to exercise for just an hour or even less. A third of a g of gravity would be sufficient to keep their circulatory systems functioning correctly and stop the pooling of fluids in their bodies, which is a major danger in microgravity. And a third of Earth's gravity is about what they will encounter on Mars, so it would help to acclimatize them and teach them how to move about safely in the Martian environment. When the astronauts reach Mars, they will have to do daily exercise to prevent muscle and bone loss, circulatory problems, and other adverse effects on the human body. How much exercise they will need to do is unclear, although there is a lot of research being conducted into how to keep them healthy on Mars. Perhaps a centrifuge or even a slowly rotating habitat might be a solution. However, studies indicate that working in just 38% of Earth's gravity could lead to bone density loss of 1 to 2% per month if not countered. Reduced blood volume and cardiac atrophy may impair explorers' ability to function effectively in Martian gravity. In addition, loss of muscle mass during the 6-month voyage and continued loss on Mars could compromise mission operations and emergency responses. As far as actually working in just a third of Earth's gravity goes, that is somewhat less of a problem. The Apollo astronauts very quickly learned how to work and move about in a 1/6 of 1 g on the Moon, although they did sometimes slip and fall, luckily safely. And as we said earlier, on the journey to Mars, if the astronauts can become acclimatized to Mars gravity in a rotating structure generating a third of Earth's gravity, that will greatly help them during their stay on Mars. Working outside on Mars presents a number of challenges: the low gravity, the extremes of temperature, the constant danger of falling onto sharp rocks. But there is another, more insidious danger: dust. Martian soil contains perchlorates, a highly oxidized compound of chlorine. Perchlorates are extremely toxic to humans. If ingested, they can attack the thyroid gland, leading to sickness and weight gain in addition to other health issues. Although the amount of perchlorates in Martian soil is small, perhaps 0.7% by weight, they nevertheless pose a real health risk for Martian explorers. In addition, the soil is made up of extremely fine, extremely sharp particles with the consistency of something like talcum powder, posing another danger. These particles are also electrostatically charged, meaning they will stick to everything, including astronaut spacesuits. Every 7 to 8 years, Mars experiences dust storms, which blanket the whole planet for weeks. Obviously, missions to Mars will be timed to avoid these global dust storms, but there is another danger whereby Martian soil can be stirred up and blown across the surface: Martian dust devils, as imaged here by NASA's Spirit rover. Even though Mars' atmosphere is only 1% of the thickness of the Earth's, it's still dense enough for these dust devils, stirred up by summer heat, to blow across the surface, elevating dust into the atmosphere as they go. Martian dust stirred up by any sort of activity on the surface can settle on solar panels, causing their efficiency to drop. It can penetrate into seals, into spacesuit joints, electronic equipment everywhere. There will need to be thorough decontamination procedures for astronauts entering the base from outside and the regular cleaning of equipment on the surface. But there's another danger from the dust: electricity. It's been calculated that rapidly rotating Martian dust devils can generate up to 4,000 volts of static electricity. This would be enough to knock out the radio of any astronaut unlucky enough to be outside when a dust devil passes over them, leaving them in an extremely dangerous and isolated situation. Martian dust, as we have seen, will be an ever-present danger for astronauts and equipment on the surface of Mars. It will be crucial to prevent critical systems for power generation, life support, water recycling and food production from suffering contamination and degradation from the dust, as well as preventing astronauts from suffering damage to their health. A rigid decontamination and maintenance regime will be of the utmost importance. Mars is an inhospitable, extreme environment, exceptionally dangerous to humans. All of the challenges we have looked at in this video can doubtless be overcome in time, but the time is not quite yet. Establishing a base on Mars is still some way off. We are just not ready, the technology unproven, and the possible effects of such a long space mission on humans not well understood. But we humans are endlessly resourceful and ingenious, so it's almost certain that one day our dream of walking on Mars will be realized. Well, we hope you have enjoyed this video. Check out the other Space Oddities Mars Month videos. You'll find a playlist called Mars Month on the channel, which we will be adding to during September 2025. Please also subscribe to the channel and watch our Tuesday live streams during September, where you can join in our discussions about Mars. You might also consider joining our Patreon community, which you will find at patreon.com/Space Oddities. Thank you so much, and we'll look forward to seeing you.